Welcome back to the fourth lecture of week 1. So, we will continue our discussion on n-gram language models. So, in the last lecture we discussed about what are n-gram language models and how do you estimate the probabilities. We took examples of a bigram language model and saw that. Today we will see some other issues in the n-gram language models, and that is where we will introduce the topic of smoothing. Then we will talk about evaluation, that once you have a language model, how do you evaluate, right? You may have multiple language models, which one would you say is the better one? Right? What is a good quantitative metric for this? And then we will see the issue about how do you generate sentences, right? We saw some examples in the last lecture about the unigram, bigram, trigram language models generating sequences, but how do you actually generate the sequences? We will talk about that. And we briefly talk about a larger n-gram language models. So, let us start with this particular issue, why we need the smoothing, right, with the n-gram language models. So, you see, when we talk about n-gram language model, it may be a unigram language model, bigram, trigram and so on. And finally, I need it to compute the probability of a word given the previous sequence, right. Now, assume that, so you always are working in a space of words. So, you have a fixed vocabulary always, because you are computing probability of a word given something, and this probability distribution, this word can take value from a vocabulary, right. So, it can take only some a finite number of values, that is your vocabulary size, right. So, now you will fix your vocabulary based on what you have seen in the data, right. So, if you have seen a word at least once, then only it will come in your vocabulary. So, that is why if you talking about a unigram language model which has only probability of a word, it will never be 0, because you have included in your vocabulary only because you saw it at least once, right. So, this is always non-zero, right. Of course, the assumption is that the dictionary is derived from the document collection on which you will compute this probability, right. Otherwise, you may always encounter a new word that is not in your vocabulary at all, right. If it is not in the vocabulary, you cannot do anything with the language models, the way we are discussing here. So, but now think about a bigram probability of wk given wk minus 1. Now, you have seen certain examples of these bigrams in your data, but it may happen a new example comes that has not been seen earlier. Okay. So, let us see, for example, suppose in training set you have seen denied the allegations, denied the reports, denied the claims, denied the request, right. And now on the test data where you are actually computing the probability, you have this particular phrase, denied the offer, denied the loan, and suppose this never occurred in your training data. So, what would happen immediately, because and you have to find the probability of offer given denied the, right, as a trigram language model. This is a trigram language model, and because you have never seen this in your training data, you will give it the probability of 0, right, which may still be okay, stand alone, but this can be part of a larger sentence where other words you have seen a lot, right. So, it may be part of a larger sentence where you would have seen the other phrases maybe more number of times, but because you are multiplying probabilities, even if one of them becomes 0, the entire sentence would have a probability of 0. So, this 0 probability always creates a problem. So, you do not want a 0 probability, you want some way to give it some reasonable probability estimate, and that is what is called smoothing. You want to smooth it out so that you do not get the 0 probabilities. Okay. So, what is the idea of smoothing? So, we will discuss very simple idea here. For example, so we have the probability of a word w given denied the, and in my training data, let us say I have seen the word allegations occurring 3 times, denied the allegations, reports occurring twice, claims occurring once, and request occurring once. So, total I have seen denied the 7 times, and with that these 4 words occur with different number of times. but I have never seen denied the attack, denied the man, denied the outcome. I have never seen that, right? But they are likely. I mean, they may not have been seen in that data, but they are likely, right? So what do I do? How do I give them a non-zero probability? So the idea is very simple, right? Your probability is anyway fixed. Your probability right now is distributed as 3 by 7, 2 by 7, 1 by 7, 1 by 7. This adds up to 1. Right? So what you can do, you can steal some probability mass from these words and give it to the words that have not been seen. So something like you will steal probability mass and generalize better. So let's say I steal 0.5 count from each, right? And I get a count of 2, like, and this 2 I distribute among everything else in my vocabulary, right? So what will happen? So these words, probability allegation, given, denied the, will start getting slightly lesser probability, but the attack, given, denied the will have non-zero probability, and this will be same for all the words. I mean putting it very simply, it can be same for all the words, but there are methods by which you can give a better estimate. So the way you do that is called add-one smoothing. So add-one smoothing, the idea is that you pretend as if you have seen every n-gram one more time than you have actually seen it. This is what is called add-one. So that means just add to all the counts. So suppose you want to compute probability of wi given wi minus 1. So the maximum likelihood estimate is count of wi minus 1 followed by wi divided by count of wi minus 1, right? That's what we saw. In add-one smoothing, what I will do, I'll add a 1 here, right? So I have added a 1 here. Now what should I add in the denominator, right? So that's why you have to understand that I will do it for all the words in the vocabulary. So probability of w1 given wi minus 1 will be count of w1 wi plus 1 divided by something. Similarly for w2, I will do w2, I think I have taken the other direction, should be wi followed by w1, wi followed by w2, right? Yeah, and I'll add plus 1 divided by some normalization. Now all these probabilities should still add up to 1, right? So by doing all that, count wi w1 plus 1 up to count of wi, so last word wv plus 1. If you add all this, it should give me g times and divide by g, it should give me the same thing that I had earlier, right? It should give me still count of wi w1 divided by count of wi minus 1. So they should still be the same, okay? So the way it is done, so you are adding a plus 1 to all. So what you have to do to ensure that it is normalized, so you are adding plus 1 v times. So in the denominator also you add a v, right? So you add a v in the denominator also, okay? So and that's how it is normalized, they add up to 1. So this is the add-one smoothing formula. So you add a 1 in the numerator, and to normalize that they add up to 1, you add a plus v. V is nothing but the vocabulary size in the denominator. So an example, like same example as the last class. So we found the frequency of question paper as 180 in the corpus C, right, based on this information. Now suppose we are given another information that the vocabulary size is 1210. So V is 1210, and what would the probability of paper given question after add-one smoothing? So add-one smoothing probability of paper given question is going to be count of question followed by paper plus 1 divided by count of question plus vocabulary size, right? Count of question paper we got as 180, so 180 plus 1, count of question we got as 600, and vocabulary is 1210. So this is 181 divided by 1810, so 0.1. So earlier the probability is 0.3, after add-one it became 0.1. This is a toy example, but typically if a word occurs in the data after add-one, its probability is going to decrease, okay? So it comes out to be 0.1. Okay. Now add-one is one particular way of smoothing, but you can do more general formulations, like rather than doing add-one, I can do add k, add alpha. So if I do add k smoothing, So what is the idea? That I don't add +1, I just add some plus k, and the k can be small value like 0.5. I will do add 0.5, right? So, and then accordingly in the denominator I'll multiply that k to the vocabulary, because I'm adding k to each word in the vocabulary in the numerator. So I'll add a k times v in the denominator. This is one way. Now another way of visualizing this is, suppose you take k times v as m, right? So then your k becomes m times 1 by v, right? Now you can see this equation in this particular form, right? And observe this equation. How do you interpret this? So you have, this is just a normalization, but in the numerator you have count of wi minus 1 followed by wi. How many times you have seen them together, plus m times 1 by v, right? So this is as if, see, what is 1 by v? So 1 by v can be a probability that you will give to that word as a uniform distribution, right? If this is a uniform distribution, each of the word in the vocabulary will have a probability of 1 by v. So this is, you are as if you are interpolating with a uniform probability, right? This count you are interpolating with a unigram probability, right? And then if you are anyway doing that, a better way of smoothing can be, so because I will add 1 by v to each word, right? But why should I do that? Why can't I add something that is proportional to their actual frequency of probability in the data, right? So rather than adding 1 by v, why don't I add their actual unigram probability, pw1, pw2, up to pwv, which will anyway add up to 1, right? So that is where I get the idea of interpolation. So I can, instead of doing that, I can interpolate with the unigram probabilities. So I can express it like count of wi minus 1 wi plus m times probability of wi. So that is called interpolation. You are interpolating the bigram thing with the unigram, right? Divide by count of wi minus 1 plus m, right? So you can do interpolation, right? So this is a very interesting idea and is also used with large language models. You can interpolate multiple large language models and so on. So in general, there is another term that comes with interpolation. It's called backoff. So you typically use backoff and interpolation. I mean, one of them. So what is the difference? So idea is that sometimes, even if you're using an n-gram language model, you may have to resort to a less context, right? Even if n is smaller, you may have to use still less context. So that means you condition on less context for context that you know less, right? So the way you do that, so one way is you do interpolation. Let's talk about interpolation that we talked about. So you mix the trigram with bigram and unigram. You mix the probabilities. So you have probability from trigram, bigram, unigram, you mix them. That is the way of interpolation. Because each of them is an individual probability distribution, you can mix them. By mixing weights should be such that they add up to 1. Then it is fine. It will still be a probability distribution. Or you can do backoff. Backoff is that if you have good evidence, you use only trigram. Otherwise, you back off to bigram, right? That means you don't have evidence for trigram. I'll just use the bigram in this case. And if I don't have evidence for bigram, I'll go to the unigram, right? This is called backoff. And yeah, generally interpolation works better, but there are scenarios where you may have to use backoff. Okay. Now coming to our point on evaluation, like how do I evaluate these n-gram language models? And this would actually be applicable to, in general, any language model that we will study in this course over the weeks. So when you want to evaluate a language model, there are two kinds of evaluation. One is extrinsic, another is intrinsic. So what is extrinsic evaluation? This is like you are trying to use it for an actual NLP task and seeing how good it performs. So let's say I have trained two different language models. To put simply, let's say one is a unigram language model, or let's say A is a bigram language model and B is a trigram language model, right? And you may have a question, which one should I use? Which one gives a better performance? Or it can be two models learned from two different corpora, right? And so on. So what you will do, so to find out which one is better, I'll actually deploy them for a real task. Let's say I apply them for machine translation or a CPG recognition, and I get scores by using model A and model B, and like I'll say how many words were translated correctly, how many words were transcribed correctly as per translation and ASR tasks. And then I can compare the accuracies for A and B and see, okay, I'll find that A always does better than B, or B always does better than A. Then I can say this model is better than another as per extrinsic evaluation. But there is also intrinsic evaluation, because you may not always be able to do extrinsic evaluation, right? You are training a model, you may want to do some intrinsic evaluation immediately rather than going for some extrinsic. So, because extrinsic evaluation, the problem is that it's very expensive and time consuming, and also it does not always generalize, because you have to use your language model and put into the application to use for something else, say machine translation. So, you need to learn how to plug your language model into that application, right? And then only you can run that. So, this may be time consuming, right? And if you have done for machine translation, maybe your language model is doing well there, but may not do well for other application. So, then typically what is another metric that is preferred, that is much more preferred, is called perplexity. That's an intrinsic evaluation metric. So, it directly measures what is the performance of the language model on the actual task for which it is trained, that is predicting the words. So, how good it is in predicting the next words. Okay. And this may not actually correspond with the real world applications, but it gives a general metric by which we can evaluate or compare language models. And it's useful for n-gram language models, and we will see even for large language models, perplexity is one of the metric that is used. So, now how do you compute perplexity? For that we will define the notion of training and test set. Okay. So, what happens? So, whenever you have a model that has parameters, you have to train that parameters, or you have to compute the parameters. Like n-gram language models, we are not training anything, we are just estimating the parameters, right? But you estimate it from some data, and that is what is training set. With language models, we will find a set from which I will learn my parameters. That's also the training set. Now, and when we test the performance, we will do it on a data that we have not seen, right? So, this is what is called a test set. This is unseen test data. That means it has to be completely exclusive, different from the training set. And why? Because we want to measure how good it will generalize on some unseen data, because in real world application, you will find data that has not been seen in the training, right? So, how would your model generalize to that data? That's what is measured by taking an unseen test set. And you would compute an evaluation metric like perplexity on the test data, and will tell you how good your model is on an unseen data. Okay. Now, how would you choose the train and test set? I mean, typically if you are building it for a task, like maybe you are building for a domain like legal domain, financial domain, you should train the language model on that particular task and domain, right? And because that is what is your application, right? But you may be building a general purpose model, then we will need different kinds of train data. I mean, then you have to have some estimate at test time what all things would typically this will be required for, what all domains it would need to be working for, right? So, you should have data that's combination of multiple such domains. Yeah, and in general purpose, it should not be just from one domain. There should be sufficient variety, like it should not be only from a single author or even a single language. Ideally, it should be from mixing multiple languages. Now, we should not allow test set sentences into training set. Otherwise, what will happen? Because language model has already seen that in the training, so it has already used that to compute its parameters, right? So, it would give a higher probability to that sentence. Yes, and this will be a falsely high probability because it has already seen that, and it will look as if your language model is good, but it will not generalize, right? And this is what is called training on the test set, and this is bad sign. So, typically we never allow the model to see the test set, right? But then you may have a question, fine, but let's say I am doing the add k smoothing, right? And I can vary k to say 0.1, 0.2, 0.5 and 1, and want to know which one works best. So, can I do that? I will vary k from 1.1 to 1, and I will check the performance on the test set and see whichever k works best, I will use that. Can I do that? So, typically even that is not allowed, right? Because what will happen, you are tuning your k based on the best performance of the test set, but then it may not generalize well to a new unseen data that you may encounter in the real world. So that's why the concept of development set comes in, that is different from training and test. Okay. So idea is that if you want to run your experiments multiple time and test, okay, how good my language model is now, right? You need some data. But if you start doing it on the test data, it will be like you are falsely tuning it to the data, right? I mean, you are just doing some experiment, testing on test data, again changing and testing on test data, and once you see, oh, I have a good performance, you stop. But it does not, but in the real world, nobody will give you that much time, right? You give the data and then keep on doing experiments. So you need to see how good it is generalizing to new data, right? So because you are noticing here what changes that make the model better. So that's why you have to run on the test set only once, right? So where do I tune these things? Like, how do I tune my k? Is equal to 0.1 is better, okay, is equal to 0.5 is better. That's why we need a third data where we can train a model and quickly verify like how good that is. Right? That's what is called development set, development test set or dev set, where you can tune such, these are called hyperparameters of your model. So you can tune such hyperparameters of the model. Okay, and then once you're happy on the dev set, then you freeze your model and then you directly see the performance of the test set, see how good it will generalize to a new ones in data. Right? That can give you an estimate. But if you tune your hyperparameters on the test data, it will not give you a good estimate. Okay. So now what is perplexity? So you have understood we have trained data and test data. So typically a good language model will be one that will prefer the real sentences, right? So you should assign higher probability to a real sentence or frequently observed sentences, but low probability to some word salad. I mean, just mixing randomly some words, right? Really observed words. So intuition of perplexity comes from, say, Shannon's game. So what is the idea? So how well can you predict the next word? So suppose this is my phrase, once upon a, and I want to predict what is the next word, right? Typically you can guess it will be time, and once upon a time, right? So now, as per language model, you would have a probability given to all the words in the vocabulary. So this is your vocabulary and all the words, and you have some probabilities. And ideally you would want time should have the highest probability, right? And then you can predict time. Now, what language models can I use for this game? So you are given this sequence and you have to predict the next word. So I need this distribution, give us a condition on the previous word. It will be estimate like bigram will say only upon a, trigram upon a, and quadgram once upon a, right? Let's say I'm using a quadgram here. But can I use a unigram language model? I cannot use unigram language model because unigram language model is not conditioned on any previous context. So the unigram language model will have the same probability at all times, right? So some word that occurs the most number of times, maybe the will have the highest probability everywhere. So it will have the same distribution, right, independent of the context. So every time it will predict the same word, right, whichever context you give it. So you have to use bigram or higher models. Okay. So a good language model is one that will assign higher probability to the next word that actually occurs. Now, so the best language model will be one that will best predict the entire unseen test set, right? So that is what is the intuition for perplexity, that I should be able to give a higher probability to the test set, right? So let's say I'm comparing two models, A and B. They are two both language models. So what we will compute? We will compute perplexity of A on the test set, perplexity of B on test set, and the better language model will give a higher probability to the test set than the other language model, right? That's the idea. So the better language model should give the test set a higher probability than the inferior language model. So how do we compute this? So you want to see what is the probability of the entire sequence. Now it depends on the test set. The problem is that suppose you want to compute just the probability, right? So what would happen? When you compute probability, it will be a multiplication of multiple probability values, and how many values you are multiplying depends on the size of the test set. So you cannot, your metric will depend on the size of the test set. If you have a higher test set, you will automatically get a lower probability, right? Because you are multiplying more numbers that are less than 1. So that's why you want a metric that is independent of the size of the test set, right? So that is somewhat per word, right? So what you can do, normalize, so you have to normalize it by the length of the test set, and that is where perplexity does some sort of geometric mean, right? So what will you do? So you take the probability of the entire test set, this is the probability of the entire test set, and then you do a power minus 1 by n, right? So why 1 by n? 1 by n is just like the geometric mean of that, and minus is just the inverse of this, right? It's the inverse probability. So the inverse probability of the test set normalized by the number of words, normalization happening in the power 1 by n, right? So this is how you compute perplexity. So you have the probability of the entire corpus to the power minus 1 by n, n is the number of words, and you can look at it in this particular way. So you do the inverse probability of the test set and take to the power 1 by n, right? So that is another way you can remember this. Okay. So now why the inverse? So this comes from the original definition of perplexity from cross entropy rate information theory. So probability range is 0 to 1 and perplexity is from 1 to infinity, right? So that means if you minimize perplexity, you are maximizing probability. So a good language model is one which has a lower perplexity. Okay. So how would I compute this? So suppose I have to compute perplexity, I have to compute this whole quantity. Now I know I have to compute it using chain rule of probability. So this will give me this particular quantity, and how will I compute it? This will depend on what is the language model I am using. If I am using bigram, this will be probability wi given wi minus 1, right, and multiply for I is equal to 1 to n. So that's what will happen in the bigram language model. So depending on what language model I am using, I will use that to estimate this particular probability, and then I can compute my perplexity. Okay. Now perplexity can also be seen as some average branching factor of the language model. Okay. So that means what are the number of possible next words that can follow any word, right, on an average. So take an example of a very deterministic language that can have only 3 words: red, blue and green, right. So any word can be followed by red, blue and green. Now assume that there is a language model A where each word follows any other word with a probability 1 by 3, right, and you have a test set data like red, 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 blue, and you want to compute the perplexity. What will be the perplexity? So you will find out the probability of this whole sequence, and you will raise to the power, there are 5 words, minus 1 by 5, right. So what is the probability of the whole sequence? You have 1 by 3 for each to the power 5, and then you do minus 1 by 5. So this will be 1 by 3 inverse, that is 3. Okay. So its branching factor becomes 3. But suppose the probabilities were distributed in a different way. Let's say red was very likely in the training. So red has a probability 0.8 and green and blue has probability 0.1. Then the branching factor will change. So what will happen? The perplexity will be, again you compute, so you have 0.8 to the power 4 times 0.1, and then you do minus 1 by 5. Okay. So if you do that, you get 0.04096 to the minus 1 by 5, and this gives you 1.89. This is even less than 2. The branching factor is less than 2. And typically you will prefer a language model which has a smaller branching factor. That means at any point of time you have a smaller set of words that can come next, right. If you have a high branching factor, that means you have a lot of different words that can come. So it's very perplexed in that sense, right. It may have to choose uniformly among any of these next words. So you will typically prefer a smaller branching factor. That's why a lower perplexity also makes sense. And so this is an example, like you take the Wall Street Journal corpus and you have 38 million words for training, 1.5 million words for testing, and you train unigram, bigram and trigram language model and see the perplexity on your test set. You will find, what was found, unigram has 962 perplexity, bigram has 170 and trigram has 109, right. So you see trigram language model is typically better than bigram. Bigram is much better than unigram language model. Okay. Now, so yeah, this is just an abbreviated history of the language models. So it started with as early as 1948 with Shannon models English, and then it went on, and now it's more about you find the probability of the next word given the previous sequence, right. So I saw a cat. You find out the probability of all the words in the vocabulary, and given the previous context, I saw a, right, and try to maximize the probability of cat, right, and that's how you train the models. Now we will discuss that in detail, but coming to Shannon's visualization methods, so what he did, so he tried similar experiments as early as 1948. So this is like what he got as a unigram language model from some text. So representing and speedily is in good art, or come can. So it's like random words that do not have connection. Bigram, the head and in frontal attack. Right. So the question is 1948. How did he get this unigram, bigrams, and all? So what he did was this. So he took a book, and you randomly. So see, unigram is easy. You can just keep one word and next word. But how do you do that? So we will explain it for bigram. So what you do for bigram? So first of all, bigram means probably to the first word given the start, right? So you randomly open the book anywhere and find a word, right? You and select a word, read it as word, right? Select a word at random on the page. Okay. Now again close the book. Again find a new page, right? Find a new page where you keep on reading until you again get this word, right? You again get this word. Once you get this word, what would you do? You will see the next word after that. Yes, you record the next word after that. So it becomes a bigram. Next word after that, you again close the book. Again you find out where that next word is present in the page and find the next word. You keep on doing that. Yeah. So this is what is called sampling method, right? So because you are randomly opening any page and finding that word, so the word that has occurring after this more number of times will have a higher probability of coming, and the word that is occurring less number of times after this will have a low probability of occurring. Okay, and that's how you can sample and generate. So for example, if you think about putting all the probabilities on a number line, so let's say after any n-gram, the probability of the is 0.06, of is 0.03, age 0.02, and so on, and you put them on a number line from 0 to 1, right? And you randomly generate a number. Let's say your number generating is, say right now you have generated 0.08. So what you will do with this random number? You will find which word is there on the number line at 0.08. This is off. You will generate off. Okay. So you will see if by this method, each word will have a probability of generation as per its actual probability. So if you get anything between 0.06 to 0.09, you will generate off. But if you get anything from 0 to 0.06, you will generate the, right? So the will have a probability of generation twice higher than off. But you can get any random word also, right, by this method. They will have a very small chance, but they can still be generated. Like here's some other example. So you may come up with this 0.66 and the word is, however, it's a very low probability. Here you may have a word that has an even lower probability, but they can still be generated, right? So you can do bigram generation. So you can randomly generate a bigram. When you start from I, you have a probability distribution. You sample a word as per the method we talked about. So suppose you sampled want. Again, after want, you have a distribution, probability of any word given want. You sample a word. Suppose you get 2, you get want 2, and so on. Generate the sentence, you get I want to eat Chinese food. Okay. There are of course other sampling methods. So we will talk about this when we will talk about language model decoding. Yes, and what they do, they avoid generating words that are very, very unlikely. Right. So they are typically generating words that are in the top part of the tail. They have a high probability. So we'll talk about these methods later on. Now there are also larger n-grams. So we have talked about up to trigrams, but there can be 4 grams, 5 grams, right? Like there is data set on COCA data set that has 1 billion words. So they have n-grams derived from that. Your Google Web and 5-gram corpus that has 1 trillion words, and they typically quantize probability some like 4 to 8 bits rather than 8-byte float. So that's how they are able to store these large n-grams. There's also a very new model, infini-gram, that came in 2024, and interestingly, it says that you can store 5 trillion words by using the concept of suffix arrays, right? And you can compute n-gram probabilities for any n. So I'll just give you a sample of what they are showing in their paper. So, you can refer that paper to get more details. So, for example, suppose you have this particular sentence starting from there, conducts research at the Paul G. Allen School of Computer Science and Engineering, University of, you want to predict the next word. Suppose you are using a 5-gram language model. That means he will use the previous 4 words, engineering, comma, University of, and you will predict the next word, right. In 5-gram language model, the count of this is 274,644 times, right. And the next word, the highest probability is given to California, 8%, Illinois 4%, and so on, right. This is what you will get. But 5-gram language model cannot use a higher context than engineering. So, what they showed in the infini-gram model, if I use the exact phrase from research up to here, it never occurs in the data. But they keep on backing off to the point which occurs in the data. They find at, starting from at, this occurs in their data 10 times. So, they use that to compute the probability. They say, okay, probability of the next word given this, and there they find Washington with 100% probability, right, and that was the correct answer, because they were able to use 16-gram model for this, right. So, this infini-gram model, how it helps, it can back off to any n, right, that is available in the data. So, it is just a variant of back off, because what it will do, so in infini-gram, so suppose I want to compute probability of wi given the previous I minus 1 words, its probability of the previous n minus 1 tokens along with that, yeah, followed by I. Now, which one will you take? So, you find out the maximum n prime such that this count becomes greater than 0. Okay. So, this count becomes greater than 0. So, that is why you backed off to the point where the count became greater than 0. If it was 0 here, I would have gone to the Paul, so on. If it was 0, I would have gone to Paul, until I find a point where the count is greater than 0, and then I use it to compute the probability, the actual phrase, and followed by Washington or any word. So, this is the very interesting idea, and they use some interesting data structure, suffix arrays for computing this. Okay. There are some nice toolkits that are available that you can try and experiment. Okay. So, and the same 3rd chapter of the Jurafsky and Martin book would be a good reference for reading about this more. Okay. So, this completes our discussion on n-gram language model. So, thank you.